Computer science is typically thought of as becoming an expert programmer, but it doesn't take many classes in undergrad to realize this isn't the entire story. In this video, I'm going to explain why this is the case and really just focus on what you will see in the undergraduate curriculum in computer science. I'll include a few example problems and many real-world applications so you have an idea of what's to come. Now, I think people get this idea of the major being all programming because computer science does involve more programming than pretty much any other major. Computer engineering and software engineering are the other two at the top of that list in no particular order. But programming isn't just what it's about. So let's start with the beginning of the curriculum, which is about learning how to program. This is probably what you're expecting. So you'll learn the command to write something to the screen, which involves a printf command in C, then your phrase. You'll learn how to declare an integer that you'll use for your program, which you could call anything. You'll learn how you can assign that integer a value and multiply or add to that variable. You'll also learn you need a semicolon after nearly every line, as you can see here. You'll learn how to do loops. For example, if you want to write the numbers 1 through 1000, you could write printf for every number individually and take up an hour or two of time. And by the way, \n just means go to the next line. Or you could write a loop that starts at 1, increments by 1 after every loop, and prints to the screen the number you're at, then stops at 1000. Coding this is so many less steps than writing every number. For those who have never programmed before, don't worry about what this means, you'll learn it later. Just realize that you can print 1,000 numbers with pretty much just these 2 lines of code. You don't need much more. And if you wanted to go to 1,000,000, all you'd have to do is change this number. So you can see how it's all the basics, the syntax, and just making your program run properly. But now let's move on to the classes you may not totally be expecting or just don't know much about. The first is discrete math, which has no lab component, just math. So for everyone asking, do I need to be good at math for computer science? The answer is yes, but it's a different kind of math than you're probably used to, and I'll explain more on this later. But I am going to go into a little depth on this class so you have an understanding of what's to come. You're used to continuous math. Given a function of x, x can be any value. You have to know how to graph it, factor it, solve for when it equals something, or whatever. Discrete math is where the variables can only assume discrete values, typically denoted as n, but not always. And this class actually involves a lot of proofs, and I'll show one real quick. On probably your first week, you could come across this problem. Prove that 1 plus 2 plus 3 all the way to n equals n times n plus 1 over 2. So let's see if this is true. For n equals 3, we get 1 plus 2 plus 3, which equals 6. Then if we plug in 3 for n, we get 3 times 4 divided by 2, which is also 6. So that checks out. It works for n equals 2 and 1 as well. But how do we prove it for all values? Well, this involves proof by induction. We know it works for n equals 2 and 3. Normally you check for n equals 0 first. And now we're going to prove it for n plus 1. It works for 1 in this case, so if it works for n plus 1, then it will work for all n. So I'll write this out again. Now for n plus 1, we would say 1 plus 2 plus ... n plus n plus 1 equals n plus 1 times n plus 1 plus 1 divided by 2. You just plug in n plus 1 where there were n's. But here we see that 1 plus 2 all the way to n was what was given to us above. So we can rewrite that, then add on the n plus 1. And then I'm not going to simplify this because I'm sure you know how, but these will equal each other. And you have proved this to be true. Seems kind of weird, but basically if you know this is true for n equals 0, or even n equals 1, then by proving it for n plus 1 is kind of like knocking over dominoes to prove the next. Proving it for every next case for all n all the way to infinity is what you just did. And you'll have to know how to do proofs with that technique. Now that you know this, you could prove something like 8 to the n minus 3 to the n is divisible by 5. So now you may be thinking, why would I need to understand this kind of math? Well, let's look at a different kind of example that applies a little to encryption. How would you find the greatest common factor of 288 and 160, the biggest number that goes into both of them? Well, I would divide by 2, because they're both even, and get 2 more numbers, Then those are both even, so divide by 2 again. And just keep going. Conveniently, 2 works every time, so we just multiply them at the end and see the greatest common factor is 32. But there's actually a faster method or algorithm to do this that most likely you haven't seen before. So to find the greatest factor of the two, you could find the remainder of dividing 288 by 160, which would just be their difference of 128. Now you'd have to find the greatest common factor of that and 160, the smaller of the two numbers above. Then just do the same thing. The remainder, if you divided 160 by 128, is again their difference, which is 32. Then what's the greatest common factor of that and 128? If you divided those, the remainder is actually 0. It goes in perfectly. And our smaller number is 32. Then since we got down to 0, we know our greatest common factor is 32. So look at that. We accomplished this in less steps here than we did here. And for bigger numbers, the difference would be even more. This kind of math allows computers to compute factors way faster. So what does this have to do with encryption? Well, if we have a word we want to encrypt, like maybe you want to secretly send a friend the message, we can change it into the numbers that represent its place in the alphabet. You then have to calculate some number to add on here, which would make it prime. So now we have a large prime number. Then you and your friend would exchange a secret key, which is also a large prime number. You multiply your prime number word by your prime number key. So if someone intercepts the message and turns it into letters, it won't make sense. But your friend would just divide the received message by the key and then translate it. So why is this hard to crack if someone intercepted the message? Because computers have trouble factoring large numbers into two prime factors. There isn't a fast algorithm. So that's why factoring quickly and efficiently has important applications. Now I do realize when it comes to encryption, this method is wrong. This isn't exactly how it's done. There's a lot more to it, and if you want more info, there's plenty of videos out there. But for this one, I just wanted to give you the tiniest glimpse as to what's going on. It never made sense to me when people said encryption has to do with large prime numbers, so I wanted to just show that. Then you will come across graph theory. And no, not graphs like x squared or sine of x. It's graphs that have a bunch of nodes or points and vertices that connect them. This has a lot of applications in computer science because of how complicated connections can get. Think of how we are all connected on Facebook, for example. Two people actually use graph theory to become billionaires that I'll explain soon. But first, a basic example. Let's say we have 5 college classes, so a really small school. Computer science 1, biology 1, chemistry 1, physics 1, and calculus 1. Some computer science students are in the physics class, some others are in the bio class, and some others are in the chem class. Then some bio students are in the chem class, and some chem students are in the calculus class. So chem and physics don't have any of the same students, same with calc and bio, and you get the idea. Now the question is, how many time slots do we need for finals day? So could we schedule one final time from, I don't know, maybe 9 a.m. to 11 a.m.? No, of course we can't, because if there's a computer science final at time 1, and the bio final has to be at the same time, those students who share both classes can't take both the finals. So could we do it with 2 time slots? One from 9 to 11 and one from 11 a.m. to 1 p.m. If we gave computer science time 1, then bio would have to have time 2, but now chem would be out of luck because it shares with both those classes. But turns out we can do it in 3 time slots. If we make another time slot, we could give computer science time 1, bio time 2, chem time 3, then physics could be time 3 because no one shares it with chem, and calculus could be time 1. But imagine what this is like for a university with hundreds of classes and thousands of students. It gets complicated. What if we have 5 chess players, A through E? And player A can beat player B, who can beat player C, who beats player A, then E beats A, and so on. Based on all these connections and who beats who, which player should be ranked the best? Or what if we looked at the 50 states? Really only the 48 that border each other. So like California borders Arizona, Nevada, and Oregon. Then those border other states, and this would go on for a while. How many colors do we need to color a map of the United States so that no 2 bordering states have the same color? Believe it or not, this was proven to be 4. You've probably never noticed, but the maps of the United States only need 4 colors so that no 2 bordering states have the same color, which allows us to distinguish the states easily. And lastly, what if the World Wide Web contained 4 websites, all on the same subject? And website A had a link on its site to B and C, which kind of means, hey, these websites are good, check them out. Then B linked to D and A, and so on. Which website should be ranked the best, assuming they are all about the same topics? Well, 2 guys studied this and created an algorithm for how to rank the sites and called their website Google. So being good at graph theory can pay off quite well. There's more to discrete math, but I'm going to move on. I think you get the point how these are discrete math problems like amount of websites, classes, factors of large numbers, and so on. This class will lead you into the design and analysis of algorithms. I'll go over the basics of this class and more in the next video.